Good evening, everyone. Welcome to today's problem solving section, course Digital Electronic Circuits, week 9. So first, we will start with the counters. So, the state of the counter will change or will be advancing with every trigger that is from the clock, and this can be random or in sequential order, such as up counter or down counter. So, and you can also design up down counter, the same counter up down counter, and also this is an increasing order and this is an decreasing order, and also in any predefined sequence also. So all the flip-flops can be triggered from the same clock, like we say that as synchronous counter, meaning to say, like I have say two flip-flops and the state changes of this and this flip-flop based on one global clock. So such circuits are called as synchronous counter circuits and asynchronous counter. And the next circuit is asynchronous counter, where say my first flip-flop is triggered from the global clock. The next flip-flop state changes as per the output of this flip-flop. Then these circuits are known as asynchronous counter. The state of this flip-flop will not change, will not depend on the clock, but it will depend on this output. So, next is the modulus of the counter. We say like mod n counter, which has n different states. So, like if we have m flip-flop, then what will be the m? We can achieve like modulus n 2 to the power m. Meaning to say, if we have some 3 flip-flops, say if we have 3 flip-flop, then m will be 3. Then the modulus of the counter, it can count up to 2 to the power 3, which is 8. So we can get 8 different states. And the next thing, usually the clock is given as the input trigger. So we use the clock as the trigger, and the mod n counter is also called as divide by n count. Okay. So this next we will start with the asynchronous counter. So first We'll So let us start with three flip-flops. And let's have as the given flip-flop is asynchronous flip-flop, let's connect the clock for the first flip-flop. And let's use taking flip-flop. Weber. And let us take all the three inputs A, B, and C. So now let's operate all the three flip-flops in the toggle. Is connected to VCC. The next clock. So, for example, if this A is applied as a clock for first flip-flop, and second flip-flop, the third flip-flop receives the clock from B. These are the outputs. Then, now let's draw the waveform for this circuit. If we consider this as the clock, input, then this is at the negative edge. So every negative edge, we will have the changes of the state from the flip-flop. So this is the clock. Let's have the A flip-flop will toggle every clock. So we can say it will be 0 1 0 1 0 1 0 1. Okay, so now this, if you see what the frequency of this FA, we observe that this clock by the next. If we want B, the B will also operate at the negative edge, but at this negative edge. A will be the clock for that. So this will be the negative edge for B. So it will be 0 0, then 1 1, 0 0, then 1 1, then 0 0. Now if we observe the frequency for this, the FB frequency will be F clock by 4. Next, let's plot for C. Now this will be at the negative edge. So it will be 0 for this time period and then 1 for this time period. So it will be 40 followed by 4. So again, this frequency is observed that it is F clock upon 8. If you want to plot it, like tabulate it, the clock C D A count. It counts from 0, 1. Say we are applying a negative edge. 2, 3, 4, 5. So you can say 1, 1, 1. Then it is again starting from 0. So after 7 it is 0. And after every this clock pulse, or let's denote the clock pulse with say B, C, E, clock pulse. So initially it is 0, 0, 0. Then A is 1. Next 0, 1, 0. 0, 1, 1. 1, 0, 0. 1, 0, 1, 1, 0. Then again back to 0. This is the up counter. Next, if we will design the down counter. So asynchronous down counter. Again, we will take 3 flip-flops and let's consider JK flip-flop. The same flip-flop with 3 outputs A, B, C. First flip-flop will be applied, triggered from the clock, and now next we will operate the all the 3 flip-flops in toggle mode. It's plus ECC fast logic 1. Next, for down counting, we will now apply A complement as the clock and B complement as the clock. So again, if we take the waveform, output waveform, all for the first flip flop is operating in the negative edge. The first waveform is our clock. Next, we will plot the A. A will toggle every negative edge. So A will be same. You will get alternative zeros and ones. So next we will plot for B. Let the B initially be 0. Next, the clock is alternative A. So instead of cos edge, now it will instead of this edge, now we will see the effect in this edges. A bar and this and this will cancel. So it is working in negative edge of A complement. So positive edge of A. So positive edge of A, it will toggle positive edge of A, toggle. Again a positive edge.
Ma'am,
Ah, yes.
ma'am, can you repeat how to draw B waveform, ma'am?
Yes, yes. It is A bar is applied to this complement, and this is at the negative edge. This negative edge and this complement will go like this flip flop will operate at the negative edge of A complement or positive edge of negative edge of A complement or at the pos edge of A. So I am considering the positive edge, and every positive edge I am toggling the B.
Okay, ma'am, got it.
So next for C, again at the positive edge it will C flip flop will toggle. So 0, the positive edge, again positive edge toggle, again at this positive edge it will toggle. So 0, 4 ones followed by 4 0. So now we can say that it is 7 6 5 0 7 6 5 4 3 2 1 0. So it's a performing down counting, and it is asynchronous because the first flip flop is triggered with the global clock and the next flip flop from this output, not from the clock directly. And here is the output. If we take C bar, B bar, A bar, then it will be up counter. And similarly in the previous circuit, the inverted outputs will be giving the down counter. Okay. So with this, next we will go for up down counter. And this is a circuit diagram for up down counter. Here the M equal to 0 will select, if we consider the mode select as M, it will select the up counting, and M is equal to 1 will select the down counting. Means like if we have 0 here, this will be inverted. This inverted will be applied here. So this will be selected, A will be selected, and this one is 0. So for AND gate, this will be 0. So here we will get the A. Similarly, here 1, here B. So this is B. Here it is 0. So this will be 0. So this will be 0. So we know to this negative edge, if we apply A and B, it is up counter. And A bar, B bar is for down counter. So we can see 0 is for up counting. Next, if we apply 1 here, this will be 0. So this gate will be applied 0. So this will be 0. And A bar, here it is 1. So this will be selecting this A bar. And here the clock will be A bar will be applied. Similarly, this will be 0. So this will be 0. This will be B bar and 1. So this will select B bar and the clock will be B bar. So it will be performing the down counting based on this mode selected. Okay. Next, we will see the decoding counter state. Here we have a decoding logic, this gate. Based on this, we are having an output Y. So now, if we are saying decoding is 1 1 1. This output will be 1 if this all the three inputs are 1, because this is AND gate. So this is decoding triple 1. So on every eighth clock cycle, y will be 1. So if we want to plot this graph of this A, B, C and the decoding logic, this is clock and A at the negative edge. So every clock cycle it will toggle at the negative edge. So this is up counter or down counter. So you can see A is connected as the clock and B is connected as the clock. So this is a up counter. And B will toggle at every negative edge of the A. And C will toggle every negative edge of B. And the decoding logic, which is A and B and C, ABC, is 1 at this edge when all the three inputs are 1. So you can see that at every eighth clock cycle. So after every eighth clock cycle, ABC will be 1 and that time Y the decoding logic output will be 1. Okay. Next we will see the decoding logic. So if you want the output to be 1 and decode for state 0, then we can have AB, A bar, B bar, C bar. And the decoding logic is this logic. So for decoding the state 0. For decoding the state 1, it will be A, B bar, C bar. For decoding the state 2, it will be A bar, B, C bar. For state 3, A and B, C bar. For state 4, A bar, B bar, C. For state 5, A, B bar, C. For state 6, A bar, B, C. And 7, A, B, C. So this will be the different if we replace this decoding logic block to detect particular state of the counter. So now if you want to have this is a 3 flip-flop counter, so it will count for mod. It is a mod 8 counter. If we have say mod 16 counter, then there will be 4 flip-flops. So we need 4 input AND gate or the 4 input logic gate in the decoding network for decoding. Next, we will see how we can remove this glitch. there is an occurrence of glitch using how can we remove the glitch using the decoding logic. So this is normal, like without, like this is with glitch. This is the decoding logic, removing the glitch. How this glitch occurs? It is in the asynchronous flip, counting, asynchronous counter, and also asynchronous counter are called as ring counter. Okay. So in this counter, if we have some propagation delay, so at this negative edge, we observed the toggling, but now if it is toggling after a certain propagation delay here, the similar way it will be in the this edge. So here it was toggling for one time delay. Now here also there is a shift of this is the edge, this is the clock edge. So again here one clock delay, again here one delay. Next B flip flop will also have some delay, and it is with respect to this negative edge. So one delay with respect to this negative edge. Again the same delay here, it will be observed here. Again this flip flop will have one delay with respect to this negative edge. So totally this is from A, this is from B flip flop, this is from C flip flop. Total 3 times of the TP delay is observed here. Now similarly if we come till here, we can see C B A bar. If this is the decoding logic, at this particular instant of time it is 1 0 and 1. This will go to 0 state, so output will be 0, but decoding will show here a small occurrence of this count, but it is due to glitch. And to remove this glitch, we will perform an AND operation with the clock signal, like A bar, B, C was our initial decoding logic. Now we will perform another AND with the clock. So, so usually the decoder is just a small, like a small combination. So this delay will be we consider to be smaller than propagation delay. So we are not showing this delay of this combinational decoding logic. So hope this, because of the clock, you can see in this region the clock is off. It is 0. So if we perform AND with 0, it will be 0. So the glitch is removed. And next is solve some questions. A mod 5 ripple counter is given below. The output of two input gate is used to clear the JK flip flops. So the input of the two flip flops is the two flip flop gate is any doubts?
No, ma'am.
Yes. You can try this question. The input to the gate is A bar and C bar. To some gate, A bar and C bar is applied. And it is applied to the clear of all the three flip-flops. And it is given mod 5 counter. So mod 5 counter means the valid states will be if we got 5 states 1, 2, 3, 4, 5 states. So this will be valid state. So at 101 we have to clear the flip flop. Both if we say A, B, C, both A and C are 1. So A, C are 1. So we want to perform clear when A and C are 1. So this will be the logic equation. And already there is one inversion here. And this will be equal to AC. So this will be C bar plus E bar. One inversion I am removing because it's already in the this inversion. So it's C bar plus E bar. And already we are applying C bar and E bar. So this gate should be an OR gate. So going to the next question. The circuit shown below functions as and it has active low asynchronous reset RD. So we are resetting the flip flop with this logic which is Q2 and Q0. So if we plot it, this will be our clock. The next Q0, again it is a negative edge. So in this edge, the output will be the flop will change the state. At all the negative edges. Next Q0. So it will toggle at every negative edge. The next Q1, the negative edge of the first flip flop output. Q2, same way negative edge of first flip flop output. Next is our clear logic. It is RD complement, which is nothing but Q2 Q0 whole complement. So when the NAND gate output will be 0 when both the inputs are 1 and 1 otherwise. So and the input to the NAND gate is Q2 and Q0. So when both the Q2 and Q0 are 1 in this state, the output will be 0 and 1 otherwise. This is applied to the clear logic. So with this you can see the flip-flop is clear when it is 101. So this is modify counter. And whether it is up or down counter, 0, 1, 2, 3, 4, 5. 5 it is clearing, so it is 0 again. So this will be cleared, right?
Ma'am, why is it written Q2, Q0 whole bar?
Because this is the clear output. The RD bar is Q2, Q0 applied to NAND gate.
Okay, ma'am, got it.
After this, the flip-flop will be clear. So it's a up counter. So answer is modify up counter. And then next question, a ripple counter with positive edge. So it is positive edge trigger. There is no bubble here. So it's a positive edge trigger. If the present state of the flip-flop is all 0, then the next state will be. And it is a T flip-flop, toggle flip-flop. So we want only one state, and it is active high, positive edge triggered. So at the positive edge, this is the clock. Let's plot Q0. Let the initial state be 0. The Q0, this flip-flop output, it should toggle at the positive edge. It is toggling. Next, Q1. So at this clock, the output will remain 0 because still it has not seen a positive edge because it is Q, but what will be Q bar? So Q bar also, that is our clock. So it's a negative edge. So Q1 will remain in the same state. Also, Q2 will remain in the same state. So output will be in 1, 0, 0 state. So next question, synchronous counters. So for the synchronous counter, we want the clock to be controlled by all the flip-flop state should change according to the global clock. So if we again consider 3 flip-flops and apply J and K to be 1, C, P bar, B, P bar, J, K. The first flip-flop, as before, controls the clock. So this is synchronous circuit. So I apply clock through AND gate, and this input is controlled by the clock. The other input is our A. Second flip-flop one controlled by AND gate, where A and B will be the input as well as the clock. So you can see here also one input is clock, here also one input is clock. So when clock is high, it is like allowing the edge. So with the edge of the clock, like the global clock, this flip-flop will be working. So here there will be no glitches. If we tablet the count, so if we consider the initial state to be 000, the first flip-flop will toggle. No, the second flip-flop will toggle in the clock edge plus when A is changing from in the negative edge. So 1 to 0. So this is 1 to 0 change for A. Here it should toggle. And at this B is 1 to 0, C will toggle. And this will be toggling every clock cycle. This is 0 to 1. So remain in state. 1 to 0 toggle. 0 to 1 same state. 1 to 0 toggle. And similarly this is 1 to 1 state. So same state. 1 to 0 here it should toggle and it will remain in the same state. So this is the synchronous up counter. The another type of synchronous up counter is like we are applying the same clock, global clock. We are not having any AND gate or any logic for this clock, and at we are applying a J and K input as per the modulus of the counter or the required counting logic. So if you see here the J is A and here it is A and B. So if you see for the first count, let the initial state of the flip-flop be 000. The next count value it will toggle. So A and B are 1 1, but so it is 1 1. So we have to write for JA, JB, sorry KB, KA, JB, KB, KC, KC, and what will be the output? In this case, it is A, B, and so initially, if we consider to toggle, K is 1 1 and A is applied to this is A and this is AB. So this is also 0 0. The next state, this will toggle, this will remain in the same state. Now this will be always 1 1. The next state will be A and this one it will be A and B. So it is 0 0. So again this will toggle, remain in the same state. Now again this will be 1 1. This is A, this is A and B. So remain in the same state and toggle. So in this way, this flip-flop will work as the this is controlled by the same global clock, so it is a synchronous of clocks. So next we will solve one question. The given circuit is or an So first, is it synchronous counter or asynchronous counter?
Asynchronous.
This clock, I'm not connecting to this particular clock. If the circuit was something like this, then
Synchronous.
it is asynchronous counter. Because this flip-flop clock is the output of the first flip-flop. So this is asynchronous counter. The next question is whether it is up counter or a down counter. We have already plotted this waveform. I will again plot it. Let's plot the values of all the three flip-flops. That's Q1, Q2, Q3, Q4, and +4. So it is negative edge triggered. Next is Q2, the negative edge of the first flip-flop output. Q3, again negative edge of this flip-flop, which is still here. So you can see if I have Q4, in this region it will be 0. So just with this, let's see whether it is counting up or down. So it is 1, 2. Next is 1, 1, this is 3. So you can see here it is 0, 1, 2, 3. So it
Up.
is
Up counter.
so it is synchronous, asynchronous up counter. So next question, consider the following figure. Suppose you are asked to make a decoding circuit, any logic gate such that the output y is equal to 1 when the counter is at state 2, 3, 4, and 5. Using a single gate, so the following is the implementation. So the output y is 1 when the counter states are 2, 3, 4, and 5. So if we consider in this order, the counting is considered as A, B, C. A has the LSB and C has the MSB. Then it is 2, 3, 4, and 5. These are the values for which the counter should be 1.
Ma'am,
Yes.
why is it written CBA, ma'am?
C has the LSB and that
Okay,
is
okay,
counting.
ma'am.
This is
Okay, ma'am,
the
got it.
decoding system. So every clock pulse, this will be toggling like 0, 1, 0, 1. And this will be like 0, 0, 1, 1. So, and this is 0, 0, 0, then 1. So if this like this is MSB and if this is LSB, considering A, B, and C, and the Y logic from this will be C, B. If I write for this, it will be C bar, B, and this it will be C, B bar. It is which is C XOR with. Yes. Any doubts?
No, ma'am.
So this gate, logic gate is a XOR gate. Next question. In the asynchronous sequential circuit, the problem of glitch appears in the decoding circuit due to finite propagation delay of the flip-flops of the counter circuit, and this can be prevented by using clock bar as an input to the decoding gate along with the respective counters output. So for this was our waveforms, and we have seen this delay is because of the flip-flop, and decoder logic delay we have assumed to be very small, so we have only showed the flip-flop delays. And we have seen for the first flip-flop, there was 1 TP delay, and next flip-flop had 2 TP delay, and the next 3 TP delay, because this was delay of A plus delay of the B, delay of the C flip-flop. And here at this point, we have seen the glitch. And the glitch was removed by performing AND operation with the clock signal, right? Because the clock is 0 here. So any glitch 0, and with the CBA bar, the decoder logic which was having glitch, was removed. This is clock. So it is clock, not the clock bar. So it should be clock, not the clock bar, and it is in the asynchronous sequential circuits only, and it is due to the finite propagation delay. So this is true. Statement 1 is true and 2 is. Next, in the given figure, various states taken by the counter are, and here also C is the MSB, A is the LSB. And this J, this is a synchronous or asynchronous counter. Here all the flip-flop clocks are connected to clock, common clock. So it is a synchronous counter. And this is A, A, B bar. So it is A, B bar. Now let's write C. C is the MSB, so I'm writing C first. C is input is A, B bar. So both J and K are same input, so I'm writing it only once. For JK, and the JK for B output is A for B flip flop, and for J and K for A flip-flop is 1. With this, what will be the output? A, B, C, B, and A. And what is the respective count of it? So initial state, let's assume it will be 0, 0, 0. This will be both 1, 1. This will be, no, it is A, right? A, it is 1, 1. And A is applied here, so 0, 0. Here it is A, B bar. So again 0, 0. So A will toggle, other flip-flop will be in same state. Now A is 1, 1. A and B, it is, here it is A, so 1, 1. Here it is A, B bar, again 1, 1. So all flip-flops are in toggle state. Next, A is 0. And A, B bar. So 0 and 0, so 0. Now this A and B should be retaining the state. Sorry, not A and B, C and B will retain the state, A will toggle. Next, what will be A and A is 1, 1. A and B bar is 0, 0. So C will retain the state, B will toggle, A will also toggle. This is 1, 1. A is 0, 0. And A, B bar. So 0 and 1. So again 0. So this will retain the state, this also retain the state, this will toggle. Next 1, 1. A is 1. A B bar is also 1. Again it will toggle all the flip-flops. The next A. What is this? A is 0, 0. And A B bar again 0, 0. So retain the state and toggle. So with this we can see it is 0, 1, 1, 1, 0, triple 1, 4, 5, 2, 1, 1. So next this should toggle. A is 1 and this is 0, 0. So remaining 0, toggle, toggle. So you can see count is not wrong. Here it is again starting from 0. So C is the correct answer. Any doubts or
No, ma'am.
next question? How many number of flip-flops are required to make mod 479 counter?
9.
Yes, because 2 to the power 9 is
Greater than or equal 500.
yes. So up to 512 states we can obtain, and so we need 9 flip-flops. And if we want to make say some 30 or 32 state mod, then the number of flip-flops required will be
5.
We need 5 flip-flops. Because 2 to the power 5 is 50. So, next question. The clock frequency of 12 MHz is applied to a cascaded counter of modulus 4, modulus 5, modulus 6. What are the lowest output frequency and the overall modulus of the counter? So we are cascading mod 4 counter with another mod 5 counter with mod 6 counter, and we have to find what is the output frequency and overall modulus. So first we will find what is the overall modulus of the counter. It is 4 into 5 into 6, which is 120. And output frequency, if we say clock is say f frequency, then it is f by overall modulus. It is 12 megahertz upon 120, which is 100 kilohertz. 100 kilohertz and 120. Next, we will see mod 3 counter. The mod 3 counter will take one input, which is clock, and the output will be A and B, 2-bit output, because it has to count 3 states. So if it is 0 0 0 1 1 0 0 1 1 0, they are the valid states. Then let's design. And we have a clock. So and K we apply plus VCC. B. And here also we apply plus VCC to this K. Now if we plot the output waveform, the first flip-flop. Yes, any doubts?
Ma'am, how are you drawing the circuit, ma'am?
Yes, I'm analyzing the circuit. I have not designed the circuit, but for simplicity, we are able to decide the stable area. We can make a expression and then do it. Now we have to
Okay,
example
ma'am.
to see these values. So this will be at the negative edge of the clock, and again this is the negative edge of the clock. So if for this circuit we want to analyze it, B A J B is J and KB is 1, JA is B bar, KA is 1 and count. So initially let's take A and B are 0 0. So JB will be 0. This is always 1. B bar 1. So this is also 1. Let it be the initial count. Next clock application of the clock 0 1. It is reset. 1 1 is toggle. Then state 2 it is A 1 B bar 1. So some mistake I have done. Yes, sorry. It is JB KB. It is reset and A is in toggle state. Now A is 1, is K also is 1. It is A bar, this is 1. So both are in toggle state. So again A 1, B bar 1. And now 0 1 is reset, 0 1 is again reset. So with this we are in the 0 state. So you can see it is counting 0 0 0 1 1 0. Now if we cascade this mod 3 counter, two outputs A and B clock to another mod counter. This will have two states 0 and 1, so mod 2 counter. This is one circuit space, yes. Now if we analyze this circuit, it will be having the valid state 0 1 2 4 5 6 and again repeating from at the negative edge. Mod 3 counter, it was 0 1 0 0 1 0 0, right? So A and B we will obtain from the mod 3 counter. This was 0 0 1. Again, 2 zeros, 1, 0. Next, C is the mod to counter. So this is given, this B is given as the clock to the mod to counter, and at its negative edge, the flip-flop will toggle. So here is the negative edge, and here is another negative edge. So with this, you can see it is 0, 1, 2, 3, 4, not 4, 3 is skipped, 4, 5, 6, and 0. So this 3 state is getting skipped in this way of cascading. Okay, next we will cascade the mod to, like we have two options, either we can have at the output or at the input. Now let's cascade at the input. And these flip-flops are operating with the toggle state. This is the clock input. Now for this combination, if we plot the waveform, so it is the negative edge trigger at every negative edge. This is the clock. Next Q, it is 2-bit counter, so it will toggle at every negative edge. Next, the mod 3 counter. A and B, I am writing like this same order. A is previously 0, 1, 0, 0, and it should work at this negative edge. So 0, 1, and 2 zeros. So this and this edge. 1, 2 zeros. And B will be 0, 0, 1. So same with 0, 0, 1. And this edge again. So it is 0, 0, 1, 1. This is 0, 1, 2, 3, 4, 5. Again back to 0 and then from 1. So here this validates the counting is 0, 1, 2, 3, 4, 5, and then again 0, 1. Here this 3 was skipped in this way of cascading. Next, This is a modify counter. So if you want to find the modulus of this counter, this will be the clock signal. JA is C bar and KA is 1. So we observe that A will be 0, JB is 1, KB is 1, so 1. So this is also 0 initially. And JC is equal to AC, AB, and KC is 1. So let's start with this state. So 1, 1 is always 1, 1, 0, 1. So the next state will be 1, 0, 0. So here also 0, 1 again. 1, 1, 1. So this is toggle. 1, 1 means this also toggle. 0, 1, reset. Next 1, 1, 1, 1. So toggle. This has the clock from A. So this is 1, 1. And here 1, 1. This 1, 1, 1, 1. Next 0, 1. 0, 1. So next this reset, maintain same state, 1, 1. So this is counting C, B, A, C out, all zeros. 0, 0, 0, 1, 0, 0. Next is 0, 1, 0. Next is 1, 1, 0. So 0, 1, 0, 0, 1. This again 0, 0, 0. That is 0. So there are 5 valid states. So it is modify counter. Now cascading this modify counter. So this is the modify counter. Now we are cascading the modify counter and obtaining the mod 10 counter. And do this. This is the clock. A will be toggling every clock edge. And B, A is the clock. So after A is negative edge. And C, it is J is A, B. it will be 0, 0, 1. And C at the negative edge of this, it should toggle. So here it will toggle. Same way if you see for this circuit, we will get BCD counter. We have just modified this connection in this circuit. Next is okay, 3 mod 10 counter cascaded will give a modulus counter. So we have 10
100, 1000.
will be mod 1000 counter. Next, a certain JK flip-flop has propagation delay of 20 nanosecond. The largest modulus of the ripple counter that can be constructed from the flip-flop and still operate at 12 megahertz will be. We know n tau should be less than t log. So 1 by 12 mega, n we don't know, and this is 20 nano. And n will be less than 1 upon 12 mega into 20 nano. Which is around 4.16. So what will be the modulus of the counter? Number of flip-flops is the n, right? It is 4. So the modulus of the counter is
16, no.
yes. Modulus of counter is 2 to the power 4, which is next question. Which of the following statements are true? Synchronous mod counter do not have glitches. We have in asynchronous circuits. This is true. Lockout occurs when a counter remains in unused state. Okay, so lockout means if we have any unused state, say in mod 5 counter, this is a 6th state. So this is unused state. In mod 5 counter. So if it is remaining in the same state, then we say that it is lockout. So it is also true. And to avoid lockout, we can include some steps in the design steps. This we will see. And counters can be used in parallel to serial conversion through time multiplexing. So the answer is all of them. So next question. The number of unused states of the counter is. So for this, instead of waveform, we will go with tabular because in J and K also we have to write J0, K0, J1, K1, J2, K2. In this line, I want to select Q0, Q1, Q2. Initially, let us consider the flip-flop to be all zeros. Next, this is 0, 1, if I consider in this order. Then this is always 1, 1. And what is this? It is Q0. This is Q0.
Q2 bar.
Yes, Q2 bar. This is Q1 and Q0. This is Q0. Wait. J1 is Q0, Q2 bar. K1 is Q0. J2 is Q1, Q2, Q0. K2 is Q0. Now, this will be 1, 1. 0 and 1, 0, 0. Again, this also 0, 0. So this two flip-flop will retain the state and this will toggle. The next clock. This will be 1, 1. This will be 1. This will be 0. No, Q1, Q0, 1. Q0, 1. Q1 and Q0, 0.
0 1 0.
0, 1, 0. Next clock. This is 1, 1. This is 0 and 0, 0. This is 0 and this is 1 and with 0. Again, this is also 0. So this will maintain and this will toggle. So this will be 1, 1. Next 1, 1, 1, 1. So all flip-flop toggle. Next clock. I think I need some 2 more please. This now 1, 1. So 0, 0, 1. Q2. This is 0 and this is 0. This is also 0, 0. So this will maintain the state and this will toggle. Next, it is Q2. This is 0. Q1 is 1. And this is Q1, Q0, 0. So this is reset and this is toggle. So you can see we have come to the state 0, 0. So the state we have used is 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and then back to 0, 0, 0 state. So the unused state are 1, 1, 0 and 3, 1. So we have 2 unused states. So next we will design the counter as a synthesis problem. So if we have, this is for the synchronous counters. If we have a counter, if we have a state transition diagram, see like this. And if we consider JK flip flop, then first we will have the value for CM, EN, AN. Then next CN plus 1, VN plus 1, AN plus 1, and what will be the K for C and for B and for A. So if we consider initial state to be all 0 and the next state will be 1. We this for separation. So if it is 1, next state will be 2. If it is 2, the next state will be 3. If it is in state 3, the next state will be in 4. If it is in 4, next state will be in 5. And in from 5, it will be back to 0. Now what will be the value of J and A? From this excitation table of J and K, we know 0, 0 excitation. From the excitation table, it is 0x, 1x, x1, x0. So from this 0x, you have to see C and Cn plus 1. Again 0, 0, 0x, 0x, 1x, 0x, x1, 0x, 1x, x0, x1, 0x, 0x, 1x, x1. This is like toggle. You can see 0 to 1, 1 to 0. So it's alternating 1x and 0x. Sorry, 1x, x1, 1x, x1. Now we have to simplify this. Bn, Bn, An. So initially we saw we were analyzing the circuits. This circuit from waveform and both tabular method and saw how many, what is the mode, everything. Now we are designing this circuit with some the state transition diagram with the specification. So the J and C input should be B and AN. So J should be B and AN. And then P, XX, then I'm filling values from this table only. Okay. KB is equal to A. So you can see AC, 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 JV, EV, 1 by. And this is the decoding logic. Now, this the unused seats is going up to 5. So 6 and 7 are unused state. 7, we take 6, 1, 1, 0. Then the previous states of the flip flop is say 1, 1, 0. Then this is 1, 1. This is 1, C is 0. So this is 1. AN is 1. AB is 1. This is also 1. Is it correct? CN bar 0, 1. What will be the state of the flip flop? It is if it is 1, 1, 0. Like 1, 1, 0 means if this should be, this is the LSB, this is the MSB. And now we should write. This is 1, 1 always. This is C bar 1, 0, 0. So 0. AN is also 0. AN is 0. AN is 0. So these two states will be retained. It will be in. This will be toggle and this two will be retaining. Now from this state 1, 1. It's clear visible. 1, 1 and 1. Now this is always 1, 1. Here it is CN bar, so 0. AN is 1. AN BN is 1, 1. Now C will toggle. This is A, B and C. So C will toggle. B will be reset and this will toggle. So you can see this is having no lock-in state, but we did not consider it in design. Okay. So, but not by design. So is this clear? Next we will consider yes.
Nothing, ma'am.
So now we will consider like what are the lock-in states. If we have say 110, it is retaining in the same state, or 111, it is retaining in the same state. These states we call as lock-in state. Now in the design itself, if we want to consider, we will want this 111, 110 to be in the 0 state. This we didn't consider, but we have filled that two columns with don't care. If you see, we have filled this with don't care. The last two as don't cares. Okay. But here we will consider into design and we will not fill with don't care, we will fill with the required J and K values. So that part of the table alone if you will write. From this state it should go to 0 and from 7 also it should go to 0. So the corresponding J and K value will be x1. From 1 to 0 it will be x1 and 0 to 0 0 x1. So JC it is both xx. So JC will remain same. B and AN. And these are both 1 1. So this alone will be changing. Previously it was xx, now it will be 1 1. So we will have quad. So our KC will be AN plus BN. And JB also is XX, so it will not change. And KB will change. So now 1 1. Previously it was 0 0. Sorry, XX. This minus. So the KB will be AN plus CN. Same way, KE will not change. It was 1. But JA will change. KA is 1 and JA we have to calculate. Um, it was not 1. It is X. Um, it is 1 X X1. Yes. 1 X X0. Here it is 0. That's why we are recalculating it. And JA is CN bar plus BN. So these are the values, logic expression, and the corresponding circuit. You can see here we have implemented those equations. For JA we needed one OR gate. Previously it was directly one. So this is with without considering the unused state, and this is without considering the unused state. Okay. With this, we will go for irregular sequence using D flip-flop. So if we have a sequence which is not a regular one, like not 0, 1, 2, 3, like that sequence, some random sequence, and how can we design such circuit? So if we consider D flip-flop, and the initial state to be 0, 0, the next state is 1, 0. If it is in 1, 0, it should be in 1, 1. And if it is in 1, 1, it should be in 1. Okay. This will be tough for writing the K map. Let's go in order. Then we will figure out this the next state. This that way also you can do, but this way filling the K map will be easier. So 0 1 we go to 1 1, 1 0 it will go to 0 0, and 1 1 it will go to 1
No,
0.
but both are the same.
Yes.
You written 1010 two times, madam.
Okay. From 0 0 to 1 0. From okay. Let it be 0 1. This is also irregular, right? 0 1 3 2 back to 0. So it is also an irregular sequence. Okay, so I think 0 2. With this I will fill, and I'm considering this as B and this as A. So or let's make it some more irregular. Okay. So it's 0 2 3 1. Yes. Then from 0 0 it will be going to 1 0 state. From 0 1 1 0 1 1. From 0 1 it is going to 0 0. From 1 0 1 1. From 1 1 0 1. And D will be same as next state. We know the excitation table of D flip flop. It is 0 0. It will follow the next state. With this, we will now write the simplify using the K map. So it is 1 1. No. State 0 0 1 1. So this is BN, right? So A is BN. AN BN. When A is 0, it is 1 0. No, yeah. And 1. So EB is A bar. You can see it is 1 whenever this A is 0. So A bar. So with this, we can get the circuit diagram. This is B N, and this is A N bar. Okay, in this way, any irregular sequence also we can design for the synchronous counter. So next question, consider the design of the counter. So determine the logic equation of J and K for the LSB flip-flop. Q2, Q1, Q0, Q2, Q1, Q0. Next state equation. And LSB flip-flop means 0, J0, K0. I will write the equation for that alone. So it is 0, 0, 0 to 0, 0, 1. Fill this in order. It should be 4, 4, 5, 6, 7. And then the next state, if it is in 1, it will be in 2. 2 means 3. 3 means 4. From 4 back to 0, 0, 0. And from all these states, it will be in 0, 0 state. Now JK. What will be the value for J0, K0, the last row? So 0, 1, 1x, x1, 1x, x1, 0x, x1, 0x, x1. So now simplify using the K1, Q2, Q1. I will simplify for J0. K0 is 1. So it is 1x, 0x, 0x. So this is the, so it is Q2 bar. Okay, with this, I will go for the next question. Consider the following notice on the sequence generator. The being number of flip-flop needed to generate the sequence of length S. So we have seen if we have n flip-flops, we get 2 to the power n will be the length of the sequence. So it should be log 2s.
Ma'am, can you repeat, ma'am, once again?
Yes. If we have n number of flip-flops, then 2 to the power n will be the length of the sequence, right? Now they have given this, if we take like log 2, the s will be the n number of flip-flops.
Okay, ma'am.
Next question. If the mod 3 counter is connected on the output of mod 2, the resulting mod 6 has a counting sequence. So this we have already seen at the output when we connected the mod. This was the sequence, right? So we were getting 1, 2, 3, 4 when mod 3 was at the output. So this is true. Next. If mod 5 is connected at the output of mod 2, then the resulting sequence. So this also we have seen, you can do the till the BCD counting. Next, 3 mod 10 counters cascaded, which is 1000. This also.
True.
Yes. So this is also true. Next question, consider the D latch. Okay, this is taken from one of the gate question. So this is a 50% duty cycle. And so if we consider, say, this has some 5 units, this also has some 5 units, then D flip flop, D latch, so at the positive latch it will transfer. Okay, so this is positive, it will start transferring this value. So here also it is positive, so it will transfer till this much. So we have to find the duty cycle for this circuit. Now this is off for 5 plus 1 6 units of time, and this is the point. So this is again 1 unit, this is also 1 unit because T clock. So this is 3 unit. So this duration is 3 units, right? Plus here, if you see, you will have 1 more unit of off because of this, and already 5 units because of this. So this will be 7. So total in this portion, if you see, it will be 7, and this will be for 3 units. So duty cycle is T on upon T total. So it is 3 upon 10, 30% duty cycle. into 100 per percentage. Okay. Next question. Modulus of the counter. Okay. We will see this question. The output of a decade counter that is clocked with 100 kilohertz signal is, so decade counter means 10 is the modulus of the counter. So output is the input frequency. If I consider this as f clock, then f clock upon the modulus of the counter. So 100 kilohertz upon 10. So f0 is 10 kilohertz. Next question. A cascade of three identical mod counters as the overall modulus. So we have three mod 5 counter. So it is 125 is the modulus of the counter. Yes, so next we will solve this question. If this is the circuit given to us, this is one. Yes, both the clocks are connected, so it is a synchronous circuit. This is one, one, Q, Q, Q bar. So if this is the circuit given to us, then to analyze, let's tabulate it. What is the value of J, 0, K? Yes,
Is it mod 2? No?
mod 3. Yes, it is mod 3 counter. So this is Q0, Q1, 1, Q1 down. At the first clock, consider 0, 0, then it will be 1, 1, 0, 1. Next clock, 1, 0. So because of this, it will be 1, 1. Third clock, it will be 0, 1, and it will be 0, 1, 0, 1. So both will be reset. So it is 1, 2, third count, and 0. I'm not writing the decimal equivalent, just counting values. So it is mod 1, mod 2, mod 3, like mod 3 count. Any doubts?
No, ma'am.
Yes. Thank you so much.